Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we'll have a quick roundup of exponentials and sequences and series. I'll go through the topics on your screen, so let's get to it so the video isn't too long. So a sequence is just like a list of numbers. What makes a sequence arithmetic is if it's of this form: a plus d, a plus 2d, a plus 3d, and so on. Each of these things here is called a term, which we denote t. So this is t1, t2, t3, t4, and so on. So you note that to go from one term to the next term, we're adding d. So what makes a sequence arithmetic is if each time you add or subtract the same number. That's what this says here. This is the recursive formula. A sequence is arithmetic if we start with t1, the first term we just call a. And this formula here says to get the next term, you take the previous term and add some number d. This number d is called the common difference. So let's look at this sequence here: 72, 65, 58, 51, and these dots mean it goes on forever. This sequence is arithmetic with a, the first term being 72. The reason it's arithmetic, it has a common difference of minus 7. Each time we are subtracting 7 from the previous term. So the recursive formula for this sequence, we just say t1 is equal to 72. And to get the next term in the sequence, you take the previous term and subtract 7. So for arithmetic sequences, you need to know how to calculate the nth term, and that's done using this formula here. Tn, the value of the nth term, is equal to the first term plus n minus 1 times d. That makes sense seeing as what we have up here. T1 is a, T2 is a plus 1d, T3 is a plus 2d, fourth term is a plus 3d, the fifth term would be a plus 4d. You can see the pattern. The nth term is a plus n minus 1d. So for this sequence up here, if I wanted to say find the 40th term, it would just be a plus n is 40. If you're finding the 40th term, n is 40. So n minus 1 is 39. The common difference is minus 7. And so it would be minus 201. So sometimes what we want to do is calculate the sum of a sequence. This is called a series. If I was going to add up the terms of this sequence, it would be called a series. Now, if I want to calculate the sum of the first n terms of an arithmetic series, I use the formula n over 2 2a plus n minus 1d. So the sum of the first n terms formula looks kind of like the nth term formula over here. You can see this, what's in the brackets, is almost the same as this, except there's a 2a. And also this summation formula has an n over 2 out the front. So let's say I wanted to calculate the sum of the first 40 terms of this series. So that would be doing 72 plus 65 plus 58, all the way up to and including this 40th term here, minus 201. It would be, so n is again 40, n over 2 times by 2a plus n minus 1d. So putting that straight on my calculator, I get minus 2,580. That's the sum of the first 40 terms. So let's now look at geometric sequences and series. So a geometric sequence looks like this: a, ar squared, ar cubed, and so on. So whereas an arithmetic sequence had a common difference, which we call d, a geometric sequence has a common ratio, which we call r. You can see here, each term is the previous term multiplied by r, this common ratio. And that's exactly what the recursive formula here says. T1 is some value a. To get the next term in the sequence, you multiply the previous term by r. So this here is a geometric sequence. It's not arithmetic because we're not adding or subtracting the same amount each time, but we are multiplying each term by the same amount each time. Now to find what the common ratio is, just take any term and divide by the previous term. So we could write 81 over minus 90. We could also write minus 90 over 100. In either case, you get the number minus 0.9. That's the common ratio, and that means that each term is minus 0.9 times by the previous term. So the formula for the nth term of a geometric sequence, unsurprisingly, it's just going to be r to the power of n minus 1. That comes from up here. The first term's a, second term is ar to the power of 1, the third term is ar to the power of 2, and so on. So let's say I wanted to find the 11th term of this sequence, T11. Well, it would just be a, the first term, which is 100, times the common ratio. Now, whenever you're substituting a negative, always use brackets, to the power of n minus 1. So n is 11, n minus 1 is 10. So I get approximately 34.87. So let's say I wanted to add up the terms of the sequence here. Once again, that's called a series. So the formula for the sum of a geometric series is a outside of r to the power of n minus 1 over r minus 1. So let's say I wanted to find the sum of the first 11 terms, this series here. So a is 100, r, again, because it's a negative, I want to put it in brackets. So r to the power of n minus 1, all divided by r minus 1. So putting that in our calculator, we get approximately 69.15. So this geometric sequence here is actually a special kind of geometric sequence that occurs when the common ratio is between minus 1 and positive 1. We call these GPs, geometric progressions, convergent, because what is happening is each subsequent term gets closer and closer to 0. We start with 100, then we go to minus 90, then 81. By the 11th term, we're down at 34. These terms are going to get closer and closer to 0. So if I keep adding terms of this series, eventually the terms are going to be so close to 0, they're not going to add anything to the series. So it turns out that if I keep adding terms of this sequence, if I keep adding this series, it will eventually reach a limit. That only happens when r is between minus 1 and 1. And to calculate that limit, we use the formula S infinity because it's the sum of an infinite number of terms, and it's just a over 1 minus r. So in this case, the limit would be 100 over 1 minus, and r was, of course, minus 0.9. And so that approximately equals 52.63. So what will happen is the series starts at 100, it goes down to 10, it goes up to 91. If you sum an odd number of terms like we did here, you'll get a number more than 52.63. If you sum an even number of terms, you'll get less than that. But as you keep adding more and more terms, the sum of this series will eventually reach a limit of 52.63. All right, let's now move on to some exponentials. So one of the things that might have been new for you this year is fractional indices. So we call this thing here a radical. To write a radical with a fractional index, the power goes on top of the fraction, which root it is goes on the bottom. So for example, if you have the cubed root of x to the power of 8, that's the same as x to the power of 8 over 3. The conversion is pretty simple, but it's very useful. And we need this when we're doing calculus. If we want to differentiate something like this, we don't really know how. We need to write it like this so we can use the power rule, move the power to the front and decrease the power by 1. All right, let's move on now to some exponential equations. So an exponential equation is where you have the thing you're trying to find, in this case x, as part of the power. So if I wanted to solve this equation here, well, let's treat it a bit like a linear equation. First thing I'm going to do is I'm going to subtract 1 from both sides. So I get 4 to the power of 2x minus 1 is equal to 64. Now, hopefully you realize that 64 is just a power of 4. 64 is 4 to the power of 3. So the only way this expression can be true is if I have this expression here equal this. I must have 2x minus 1 equals 3. Add 1 to both sides, divide by 2, you get x equals 2. But unfortunately, not all exponential equations are that simple. The answer here is not always going to be a power of the thing you're trying to find here. When that happens, you need to use graphics calculator or logs. So let's look at a worded question. Number of new coronavirus cases increases by 5% each day. After how many days will the number of cases double? So it doesn't actually matter how many there were to start with, because we're just looking at when that number, whatever it is, doubles. So to increase by 5% each day, that means each day the number of cases is multiplied by 1.05. 1 plus 5 over 100 gives you 1.05. When you multiply a number by 1.05, you're increasing by 5%. So what we're trying to find is how many times I need to multiply 1.05 by itself to equal 2. Because if you multiply a number by 2, it has doubled. So let's now solve this exponential equation here. Well, of course, 2 is not a power of 1.05. We can't use the trick that we used up here. So there are two ways you can do this. You can use your graphics calculator. You can graph y equals 1.05 to the power of x, and y equals 2, and then use your graphics calculator to calculate the point of intersection. Whatever the x value is of that point of intersection, that's your solution. But a lot of people don't like using that. Instead, they prefer to use logs. So what you do is you write x equals log. So it's log of the answer, so in this case log 2 over log of the thing that was being raised to the power of x. You can put that straight on your calculator. So the answer we get is about 14.21, putting that on our calculator. So that means it's going to double after 14.21 days. So we just round that up. We'd say it will double after about 15 days, because this answer of 14.21 means it hasn't quite doubled after 14 days, but it will have slightly more than doubled after 15 days. All right, this leads us into exponential modeling. So exponential modeling is just where you're modeling real-world phenomena with an exponential equation. So the exponential equation we use is y equals ab to the power of x. A and b are just constants. A is the initial amount, what you started with, and b is the number that tells you by what percentage you're increasing or decreasing. So in our previous example of coronaviruses, b was 1.05. So this is an exponential equation because x, the unknown, is part of the power. So let's say the population of a town is 20,000 and decreasing by 2% each year. So the equation for that would be y equals 20,000, the initial amount, times 0.98 to the power of x. So here, y would be the population, x the number of years. Always let x be the time variable. So we chose 0.98 because decreasing by 2% is the same as timesing the number by 0.98. Finding 98% of a number is the same as decreasing it by 2%. So let's say I invest $40,000 at 3% per annum interest compounded annually. So this is an example of an exponential growth if you invest some money that's compounded annually. So the amount you have, let's let y be the amount you have, would be the initial amount times by, so this time we're increasing by 3%, so b would be 1.03. When you increase number by 3%, you times it by 1.03, and that would be to the power of x. So here, again, y would be the amount you have after x years. All right, let's now look at an example where we use two data points to find this exponential equation. So let's say the value of a house appreciating by the same percentage each year. Appreciate means going up in value. So let's say the house is worth this much after 10 years and this much after 20 years. We're going to find how much it would be worth in 25 years' time. So the only way I can find what it's worth in 25 years' time is if I have my exponential equation. The initial amount times the rate of increase or decrease to the power of x. Now, I'm not told in this example what the initial amount is or by what percentage it's increasing each year. I need to use these two data points to find A and B. So the first data point I have, I'm going to let x be the number of years. Remember, x is always the time variable. So when x is 10, y is 443,492. So that's one value I'm going to sub in. And then the other one I'm going to sub in is when x equals 20, y equals 596,017. So what I'm going to do is substitute in these 2 points, both an x value and a y value. I'm going to substitute them into here, and I'm going to end up with simultaneous equations. So I want to solve these two equations simultaneously for A and B. So for the simultaneous equations you did in high school, we always added or subtracted equations, but we don't want to do that here because the two things we want to find are not being added or subtracted, they're being multiplied. So where we undo multiplying is dividing. I'm going to divide one equation by the other. To make it easy on myself, I'm going to divide the one with the larger power of B by the smaller power of B. So I'm going to divide this equation by this equation. So we're going to do it one term after the other. So dividing this number by this number gives me a really long decimal, so it's about 1.3439. Now the reason I'm dividing here is if I divide A by A, the A's just cancel out. That's what I wanted. I wanted to eliminate one variable. B to the power of 20, divide B to the power of 10, you keep the same base and subtract the power. So get b to the power of 10. So I can figure out what b is easily. It will be the 10th root. The way I undo raising to the power of 10 is by taking the 10th root of this. So the 10th root of my answer, 1.3439 and so on, I get almost exactly 1.03. So that means the value of the house must be increasing by 3%. What I found is the value of the house increased by 34.39% in 10 years, so it must be increasing by 3% each year. So I can easily find what A is by substituting this back into one of the equations. Either one doesn't matter. So let's say I substitute it in here. So I could get A by itself from this equation by just dividing by B to the power of 10. So A would just be 443,492 divided by B to the power of 10. And that gives me about 330,000. So now I've found A and B. I've found that the value of the house after X years is the original amount times by 1.03 to the power of X, where X is the number of years. So that's the hard part done, finding the equation. Now finding its value after 25 years is going to be really simple. So all I need to do is take my X value here and change it to 25 because it's been 25 years. And the answer I get is about 690,947. That will be the value after 25 years. All right, thank you so much for tuning in. Best of luck studying, but you'll be fine. You're a superstar. You'll ace it, and I'm with you 100%. Thanks for tuning in. This has been the luckiest maths teacher in the world. Have a great day.